Are we good sound-wise? Oh, yeah?
Yeah. Hey. Hello. Good afternoon, everyone. My name is Maple. This is my 4th year on Team 2056. If you have any questions throughout the day, feel free to ask me. I'd like to introduce our presenter, Tyler Holtzman, presenting Design in the Modern Era.
Thanks, Maple. If you have any questions over the course of this presentation, please just throw your hand up. I want lots of questions, lots of audience engagement. So please ask lots of questions. So let's get into it. Is this thing working? There we go. Who am I and why are you listening to me? My name is Tyler Holtzman. I've been the lead design mentor of 2056 since 2007. Before that, I was a mentor and student on Team 1114. In my professional life, I'm a senior design engineer for Lakeside Custom Machinery. We build custom automation and equipment for the food industry. So it's really a lot like FRC, except instead of a game piece being a foam disc or a piece of PVC pipe, it's a chicken breast or blueberries or whatever food stuff. So yeah, kind of neat. Under the previous regulations, and you see the motor selection on each individual mechanism is unique. And you look at this thing, and it's like Kraken. They're literally all Krakens. So big change in FRC motor rules. So let's look a little bit at the sim motor. Was the kind of the previous like gold standard motor that everyone put in their drivetrain because it was the best, the most powerful, the most robust motor, comparing it with a current day Kraken X60. So old sim motor, 53 RPM, Kraken XC, 5,800 RPM. Okay, so it's a little bit faster. Old sim motor, 337 watts of peak power. So that's about a half a horsepower. That's a lot. Kraken X60, 1,400 watts. So it's like literally 2 horsepower of peak power. So it's like literally 4 times more powerful for the same RPM. Double the stall torque, 3 times the stall current, and you know, a sim motor with a Talon or an old Victor, it was about 3.1 pounds, and nowadays a Kraken X60 is 1.2. So you've got like 2 pounds of savings per motor, and you get a robot that's got like 18 motors on it, 36 pounds of weight savings. So we have like these unlimited, ultra powerful, uber lightweight motors compared to what we had just a few years ago. And then last year, they thought, well, the Kraken X60 is good. They'll love the Kraken X44, which is just kind of a smaller, scaled down Kraken. And if we look at the stats comparatively, it's a little bit faster, but still like more than double the power of an old sim, and equal torque, even though it's a much smaller form factor motor. And it's only 3/4 of a pound compared to an old sim that was like 3 pounds. So we have this crazy lightweight, uber powerful motor. And these are kind of the 2 motors that we will use for just about any mechanism. So what does all that give us? Unlimited power. Well, not really unlimited, but we have way more power than we used to before 2019. But it's not just that we have way more power. Like a sim motor itself was a great motor, but with motor you need control. So these new motors that we have now have built-in motion control, built-in velocity control, current limiting, external sensors, support for external sensors, limit switches, whatever. We have way more controllability within the motors that we have now. So not only are they way more powerful, but you can do so much more precise stuff with the motors that we have now compared to a Victor with a sim motor and an external mag encoder, previously. Questions on motors? There's nothing wrong with brushed motors, by the way. They're still workhorse motors. They work great. Um, Brushed motors, there is some degradation in their performance across their lifespan because you have these physical brushes that are pressed against the commutator of the motor, and they get a little bit dirty as they wear, and then you have not quite as good electrical conductivity between the motor. So the performance of the motor does degrade a little bit over its lifespan. With the brushless motor, we don't have that. So it means that you can reuse brushless motors year over year over year without seeing a degradation in your performance. Back in the day, teams used to swap out their sim motors before the championship because after they've competed at a couple of events, they're starting to see the robot looking a little bit sluggish around the field. Then they'd throw in fresh sims and they'd be going again well at the championship. But now with brush motors, that's really not an issue. You can reuse motors year over year again without any kind of degradation in their performance. Um, Questions on motors? No questions on motors. Okay. So the next thing we want to talk about is the sort of proliferation of COTS swerve. Um, so there's four great vendors for swerve drives that are available in Swerve Drive Specialties, West Coast Products, Rev, and ThriftyBot. They all have very comparable offerings, and they're all very good in their own right. Some of them have pluses and minuses. Some of them are a little bit lighter. Some of them are a little bit less expensive, but they're all generally very good. There are no, bad swerve drive. There are no bad swerve drives from these four vendors on the market right now. So they're all very good. And at the championship this year, 100% of the teams participating in the elimination rounds used swerve. So if your goal as a team is to be competitive in this day and age, you have to use swerve. Unless we get a game where there's like weird terrain or something that you need to traverse, or some unique game challenge where a caught swerve just doesn't work, swerve is the way to go for any team that wants to be competitive on the field. So what did caught swerve do for chassis design? Well, it made it really simple. Like your chassis now is like 4 tubes and a plate on the bottom, and that's your whole chassis. You look at some of these old robots up here, and we had these like elaborate sheet metal chassis with the wheels and everything all integrated into them. And we did that because we had lots of sheet metal resources and we could do that stuff um, quickly and efficiently, and it worked for our build philosophy. But it was a ton of resources that we poured into building these very elaborate chassis. And now that we have caught swerve, our chassis is like a joke. It's 4 tubes and a plate. So, fabricating and getting a chassis running is actually quite easy now. Robots are faster and more maneuverable than they've ever been. The 2023 and 2024 games were particularly bad for midfield collisions, where teams' chassis would end up getting damaged because we had 2 robots going so fast at each other and then colliding, and then something's got to give. The nature of the 2025 game made it so that robots weren't racing across the field to get game pieces. Everybody kind of stayed at home in their own little zone. So we didn't see the big collisions in 2025 that we did in 24 and 23. But next year's game is a new game, and it's important not to forget the lessons learned in 23 and 24. Robots must be robust electrically and mechanically. And because we have these wicked brushless motors and super fast swerves that are super fast, robots are hitting each other harder than they ever have. So it's more and more important to be robust both mechanically and electrically. Which begs the question, how fast should my robot go? Well, this is a generalization, but for most teams in most games with the swerve drive and the motors that we have now, about 15 feet per second is the right answer. You could have gone as slow as like 12 feet per second in 2025, and it really wouldn't have affected your game very much. Whereas in 24 and 23, going fast was a big advantage because we had this really long sprint back and forth across the field to get game pieces. So when we got long drives, we want to go a little bit faster. If you're doing more shorter drives, then your top speed doesn't really matter very much. And there are some advantages to making your robot slower. You have less current draw when you drive around. You have better acceleration. And you have better controllability because your robot is mechanically geared to go slower. So you have more low speed torque for maneuvering and things like that. But as a good starting point and rule of thumb, for most teams, about 15 feet per second is right.
How fast did the robots go in 23, 24?
So 24 was geared for 16 and a half. 23 was geared for 15. And at some points, we wished it was a little bit faster. And then this guy was geared for 15. And it could have gone slower. It was faster than it needed to be, really. But that one we went one gear ratio up. Yeah, all those reasons. Oh yeah, all those reasons too. So 2024 was a particularly rough game that had a lot of impacts. So some frame members were sacrificed along the way. Yes, question in the back. I'm glad you asked that because, and I'll get to it in a little bit, but one of our rules of thumb is we always support frame members mid-span now. We didn't always do that, and we regret not always doing that. So yeah, 2024, that robot was built, supported mid-span, and had a very robust structure to it. We didn't. All of these weren't us. Um, some of them were. Most of them were us, but not all of them. But yeah, we support all frame members mid-span now. Power management. In the modern era, we have these uber powerful motors that can suck so much energy out of the robot that it's important to put reasonable current limits on your drivetrain motors and really on all motors so that you're not browning out your robot as your battery starts to degrade. Um, so in 2024, we had the very aggressively fast geared robot, which was also like a major power hog. So it was, if you got into a pushing match with that, the robot would brown out, and then your robot starts stuttering down the field as the Rio browns out. It cuts the voltage to all the motors. The battery voltage recovers. Your driver is still pressing the stick forward. All the power goes back into the motors. The voltage drops again. Your robot browns out again, and then your robot goes all the way down the field. Nobody likes that. So we want to put reasonable current limits in to prevent the Robo Rio from browning out. And these are important um, with pretty much every mechanism, but it's particularly important if you have a very, very aggressively geared drivetrain, like a L3 swerve. So these are actually the current limits that we used in 2024. I believe they were the same in 25, but we were geared slower, so the issue was much less pronounced. And you didn't have like the full field sprints, and the game was just less power hungry in general. The other thing we do is we put some rate limits on the uh, velocity of the chassis so that if you crank the stick forward, the robot actually gradually kind of accelerates. And the limits are very aggressive. It's not like a slow ramp up. It's like over a quarter or 3/10 of a second, it ramps up from full speed to zero. And even a small ramp rate like that will greatly reduce the big current spikes you get when you suddenly apply throttle. So having some rate limits, even if they're very aggressive, helps a lot. If you make these rate limits too low, then your chassis will behave very sluggishly. and your robot will be slow to respond and it'll be difficult to control, and it'll almost feel like it's lagging for the driver. Questions on that? Yes. So deceleration is just acceleration in the other direction. So there is only one limit. And the limit is fast enough that the robot couldn't physically decelerate that quick enough, even if we tried. The wheels would just skid and you would end up kind of sliding. So we just have one limit and it works both ways. I mean, that limit is about 600 inches per second per second. And that robot goes about 200 inches per second. So it takes about 300 milliseconds roughly for the commanded robot velocity to go from 0 to full speed. So that's a very aggressive limit. Like 300 milliseconds is, well, very fast. If you get a stopwatch out, I doubt you could actually click it twice in 300 milliseconds. More questions? Okay. So a bit about chassis requirements. Chassis must be robust. Robots hit hard, and your chassis must be robust. This is the 2024 chassis, which is not here. Thank you, 2023. I'm glad you remember. You'll notice, if you can see, this front frame member was not supported in the middle. Our last qualification match at the champion. No, it was like a practice match after our last qualification match at the championship. Both. That frame member took a really big hit corner to corner, and that frame member bowed in, sheared all the rivets off the bottom plate, and was like folded right in. So then we had to like frantically replace it right before the elimination rounds, which is never fun. So as a rule of thumb now, we always support all frame members mid-span. If you look at this robot particularly, there's a big 2x2 that runs across the whole width of the chassis. The front end, the intake end, is actually this like massive sheet metal structure, and then the back side is a 2x1, but it's got these two like 3/8 thick aluminum ribs in the middle of it that back up that frame member in the middle of it, supporting it mid-span to take an impact in the middle. Yes.
We run with larger and tighter space limits.
Yes, we also do larger and tighter spaced rivets than we used to do. The rivets on the bottom plate are massive. They're like 1/4 inch rivets, and they're like every inch. So it's a lot now. So we want to have a low center of gravity. If you can see in this image, there's this blue. The rear frame member is shown in blue here. That was actually a 2x1 solid steel bar with the holes for the swerve modules and stuff drilled into it. And we had this, the bar weighed like 12 pounds, and it was right at the very, very back of the robot because that robot had a big arm that reached way out forward. So we wanted to make sure that we had, weight in the very back of the robot so that we wouldn't tip over forward when we reached out. You can also see the battery was also in a little cradle right in the very back of the robot to keep the robot weight back when we're reaching way, way out forward. Yes.
You guys ever
Yes. So the question was, do we ever have to lighten our chassis for weight? If you look at the 2025 robot, it was a lot of lightning holes in it. So 2024 to 2025, that's a good segue there. FRC dropped the weight limit from 125 to 115. So we lost 10 pounds of weight. And the 2025 game challenge dictated much more elaborate robots than the 24 or 23 game had. So we had big elevators reaching up high to score the coral on all levels. We had elaborate grippers that could hold coral and algae. Plus we had hanging, which was usually an entirely separate mechanism. So robots just in general in 25 were a lot heavier than they were in previous years. But we also had 10 pounds less to work with. So there's a lot of lightning holes in this thing, including the chassis. And we were very careful about where we put them to minimize the impact, remembering the lessons learned from 24 and 23. Your chassis design, you want to make sure that it has flexible options for mounting stuff. So your chassis gets you around. The stuff you put on top of your chassis is what does the stuff you need to win matches. You want to make sure that you can mount mechanisms flexibly. So, you can see how this chassis had arms, tubes that came down to the edges that mounted the A-frame, and that was a nice way to do that. You can see some examples here about how these side plates are bolted to the chassis for mounting the intake. And then there's a bunch of stuff that's bolted to the bottom plate. The elevator has a 2x1, and the elevator side plates that runs across the bottom of the chassis, and the base plate is all tied to that. And then the elevator has got these little knee braces that come down to these sheet metal supports on the front. But you want to make sure that your chassis has got good ways to mount stuff to it, like bumpers. So the kind of gold standard for chassis is 2x1 tubing. That's what almost everybody uses. We actually did 3x1 on this one. If you don't have any ground clearance constraints, like stuff that you have to drive over, with the SDS modules, you have about 1.5 inches of ground clearance stock. So you can actually make your frame member 3 inches deep and still have a 1/2 inch of ground clearance. And a 3x1 in bending in the 1 inch direction is still about twice as strong as a 2x1 in the 1 inch direction. So even though, like, you've still only got 1 inch of frame depth the way that it's going to bend in, the 3x1 versus the 2x1 is about twice as strong this way. 50% stronger. Sorry, half again stronger. So you can use 3x1. The base plate, lots of teams do plywood, and that works. The big function of your base plate is to hold your chassis from parallelogramming this way. So it should tie all chassis members together so that your robot doesn't like rack side to side. It should stop your robot from torsioning this way and provide a place to mount stuff, electronics. You want to put the battery in the very, very, very bottom of the robot. You want to put all of the heavy things right down on the base plate. So 1/16, 1/8 aluminum is a good way to go. We did 1/16 last year for weight. We were started off planning for 1/8, and then when we got towards the end of kind of week 2, when we were getting ready to release the design for manufacturing, we were like grossly overweight. So that was one of the first things that went. Generally speaking, your bottom plate is the best place to have weight. It is 1 inch off the ground. And if you're going to have one thing that's heavy on your robot, you want it to be the base plate. So make your base plate as thick as you comfortably can in order to make weight. I would have loved to have a 1/8 base plate on that, but we couldn't do it because of weight. So it's a 16th, and it's much flimsier. 24 and 23 both had 1/8 base plates on them, and that's a lot nicer. You want to think about ballast. If you know you're going to be way underweight, throw some blars of steel in the bottom of your robot to make sure that it is stable. With the motors we have now, there's not a huge advantage in being substantially under the weight limit. So if you have weight available, you should use it for stability, for stability predominantly. This like the previous years we were sticking steel bars on the robot, and then this year we were drilling 7,000 holes in it in order to make weight. So it's a little bit game dependent, and the weight reduction last year really put a damper on things. And then, oh yeah, support all frame members mid-span. That's an important one. A little aside on robust electrical practices. Because the 23 and 24 games were so rough, we learned a lot of painful lessons about making sure that our electrical connections are connected robustly. So we 3D print a lot of little doodads and stuff in order to have robust cabling. So you can see in this photo, there's a radio here that has these two little 3D printed saddles on it where the Ethernet cables are plugged into it. And then there's a tie wrap cranked around the cable immediately behind the connector. So even if you grab that cable and tugged on it, the connector is still in. Yeah, you can see it here too. These are all tie wrapped right here, right at the radio. So even if one of these gets tugged on, they're not going anywhere. Ethernet cables, it's a good idea to put a dab of hot glue on them. One of my big beefs with FRC is the RJ45 plug. The RJ45 plug is great for your home router that's sitting on top of a cabinet beside your TV. It is not great for an industrial robot that's whipping around the field at 15 feet per second, smashing into other things. So we take the time to zip tie these all down. We put a dab of hot glue on them so that connection's not wobbling in there as your robot bounces off other robots. Really just making sure that we have really, really robust electrical connections on everything is really important. We 3D print this little shroud that goes over the back of the Krakens that keeps the cables tucked in nice and tight, and then put a tie wrap around the whole thing. But just all these little things that we can do to try to make our electrical system more robust makes a big difference. Questions? No questions. Okay. Pneumatics. Lots of people seem to think that pneumatics are dead in the modern era. Most of them would be right. But there are still some use cases in FRC where pneumatics make sense. For one thing, compressed air is a source of energy that you have on your robot that is not the main battery, which is powering the 18 Kraken motors you have around your robot already and barely browning out for most of the time. So it's a second power source that you can carry into the start of the match, other than your battery. They're simple. Pneumatics have been around in FRC since the dawn of time. And for simple actions, a linear mechanism that just goes in or out, a pneumatic cylinder is really handy. They're widely used in industry. They're very, very common. So it's good knowledge to have if you're entering, a career of automation. But yeah, they're nice for certain applications. There is a kind of starting cost that goes along with it, being you need a compressor, you need a pressure switch, you need a regulator, you need a storage tank. So you need all these things to get started with pneumatics. But then once you have them, adding an extra cylinder to do some weird little mechanism that pokes out the side of your robot, or this little flicky thing that knocks a ball off the whatever, those are really easy once you have air on board. If you don't have anything else that already needs air, then it's a lot to add for one little doohickey. But pneumatics still have their place. And there's some really cool things that you can do with pneumatics that have unique properties that you cannot accomplish with an electric motor. This robot had pneumatics for a single mechanism on it. And the reason we did this was because the robot was way underweight. So we had enough weight for a compressor, pressure switch, regulator, air tanks. And we needed a simple two-position linear mechanism that was going to lift the robot off the field at the end of the match. So we've got a pneumatic cylinder that actuates this hook up and down. And we used a spring return single solenoid to control the position of the hanger up and down. And what's unique about a single solenoid is you energize the solenoid to shift the valve to extend the cylinder. And when you de-energize the solenoid, this valve shifts back and the cylinder retracts. Well, at the end of the match, your robot is disabled. The power is cut to your robot, but they don't cut the air to your robot. So the way the hanging rules were written in 2024, your robot had to be off the ground 5 seconds after the match ended. So because we did this pneumatically controlled hanging arm, we could lift the hanger up, drive to the chain, hit the chain at the buzzer sounds, the match ends, then the hanger comes down, lifts the robot after the match is ended, and we still get the points for it. So we essentially bought ourselves an extra 5 seconds in every match to do other stuff. So pneumatics have some unique properties that if you take advantage of them, you can do some cool stuff with them. More questions? Okay. Some tips on robust pneumatics practices. So you notice this video. In the bottom of the corner here, there's this little collision, and then everyone around this robot lurches back in fear. Basically, the one robot had their accumulator tank, their storage tank for air, mounted like directly on the corner of their robot. And another robot had their intake out, grabbing a ball, and the two of them collided, and the intake, the air tank exploded into about 1,000,000 pieces. When this happened, I was standing off camera, just like right here, and like bits of plastic just went flying everywhere. So if you're going to use pneumatics, put your storage tank somewhere where they're not going to get hit. On this robot, the storage tank is stuck in here in the very, very middle of the robot, not on the back corner where it could get hit. We want to make sure that pneumatic cylinders, if you're going to put them somewhere, they're somewhere where they're not going to get hit by another robot. And just as a rule of thumb for to make things a little easier to follow, we make the extend of the cylinder blue and the retract of the cylinder red. So we color code our tubing blue, extend, red, retract. Some more little tips. Most pneumatic connections use a push to connect fitting that's got this little collet on it. We 3D print these little like C-clips that pushes on the collet after you insert the tube. To get the tube out, you have to push this collet in and then pull the tubing out. So by putting this little 3D printed clip on there, it stops the collet from retracting. So you have to pull that little clip off before you can get the thing apart. So if you have a connection that's buried inside your robot and somehow it gets hit and depresses that collet, the airline can't pop out. These little tubing cutters, you can get them on Amazon or from Automation Direct. They've got a little V guide in the bottom of them so that it holds the tubing nice and square. And then it's got a really sharp knife that comes down and cuts the tubing really, really nice and square. These push to connect fittings, if you don't have them cut square, they can leak. So it's really important that you cut the tubing off square when you're plumbing your robot. One thing that we did in 24 is we had this big monster storage tank of air. And then during the match in teleop, we just disabled the compressor altogether. So that even if we lost air pressure catastrophically, the air compressor wouldn't just be running nonstop for the whole match. And we would just charge the thing before the match and then drive around with it full the entire time and then just use the air in the last like 3 seconds. So you could just carry this big energy store around with you until the last 2 seconds of the match and then use the thing. And if you take all these steps to plumb your pneumatic system well, you can have no leaks at all in it. Like back in the day when we used to ship our robots, we once shipped our robot to the Waterloo Regional, took it out of the crate 4 weeks later, and it still had 85 psi in it. So it's still like almost full 4 weeks later. Questions on pneumatics? I could do a whole talk on pneumatics. They're super cool. Yes. There is no tank for pneumatics on this robot. There was no application that justified putting pneumatics on this robot, and we were really, really tight for weight already, so there are no pneumatics on that robot. Yes. Compressor is about 2.5 pounds. The accumulator tanks, depending on what you use, can be quite small or can be quite large. You can't really see that one, but that one has this huge aluminum tank on it, and it weighs like 2 pounds or something. It was surprisingly light, but you're going to need realistically 6 to 8 pounds to get started with pneumatics. And then after that, adding cylinders. The cylinders are very light. The cylinder is generally lighter than a motor. And if all you're doing is like going back and forth between two positions or a little like pneumatic lock or something like that, then pneumatics can make sense. More questions on pneumatics? Yes.
I would want to see how is a load of old pneumatics? Like, do you know how like really old pneumatics
Do they still work and do they leak?
I don't think they're just really old.
Okay. Well, I mean, cylinders don't go bad. They don't like have a shelf life that or a best before date. So, like, we have a drawer of random old cylinders that we use for prototyping and wigging some weird thing together, and they're all fine. Usually, cylinders fail in FRC because someone smashed into them and like physically broke them or bent the rods or um, well, those are the main ways that they fail. But if they're still good and they don't leak, then yeah, go for it. More questions? Okay, moving on. Brief aside on preventative maintenance. So you're at your district or you're at the district DCMP or you're playing whatever tournament it is that you're playing. Before and after every match, you should be doing checks on your robot to make sure that everything is behaving the way that you're expecting. So we have a routine check that we go through, and it changes a little bit depending on the robot and the year. But generally starts with checking the drivetrain to make sure the wheels are all doing what they're supposed to be doing. They're pointed the right directions. Their wheels are all spinning. Um, we go through all the drivetrain, and then we go through all the functionality in the robot. So for this guy, we did wheels all around. Then we did the intake down, intake up. We'd go intake down again, and then we'd shove a coral into it, and then it would convey all the way through the robot. And that kind of verified that all the sensors and motors and everything through the whole coral conveyance system here was working as we expected it to. Then we'd put the elevator up, put the elevator down, spit the game piece back out, grab an algae, and then put the hanger through one cycle. And that would verify that all of the mechanisms, all of the subsystems, all of the sensors, all of the stuff that makes that thing do its thing works. And we would do that before and after every match. We want to be doing a visual inspection. You want to be having a look at your robot and make sure that shaft isn't bent or this cable track is disconnected up here and it's about to get ripped off or whatever that thing might be. You want to be having a good look at your robots to make sure that they're still in one piece.
One thing that people might not know, but at the scoring table of every event in Ontario, we have a little wooden box, a cart box. And after every match, the reset crew and supervisor look around, we pick up bits and pieces. By the end of the event, there are dozens of bolts, nuts, stop cones, spacers, USB cables, safety glasses. It's amazing what stuff comes off the robots. I'm thinking,
Yeah.
like, I hope this team didn't need this bolt for something important.
Yeah. I once put a robot on the field and I found half of the fork for a swerve module and like the axle for the wheel, like just laying on the carpet. Like, how do you not notice that? So yeah, we want to be making sure that our robots are in good peace. We want to be looking. We want to be listening too. FRC robots have a very distinctive sound to them. And you'll get to know your robot and what it sounds like. And if you come in one day and it suddenly sounds different, something has changed. I always tell my students that the robot will talk to you if you listen. So use your ears. If there's like some new clanking noise or some new grinding noise, stop and figure out what's going on because something's probably about to let go. Every match, we want to be putting a fresh battery in. Every match, we want to be charging our pneumatics. Periodically, you should be checking bolts on your robot. Now, some years you have some mechanism where two bolts chronically come loose. Well, tighten them up. It's really embarrassing, like when your arm falls off or something. Yes, questions. How often do you change tire tread? That's a great question. It depends on the game. The 2025 game, there was very little scrub to driving. 2024, you had a lot of battles with a defender at the loading zone or at the scoring zone. So there was a lot more just wheels slipping on carpet. So there was a lot more scrub, and tread would wear a lot faster in 24 than it did in 2025. The last couple of years, we've been using the black nitrile tread on our SDS swerve modules, and we generally get one event out of a set of treads. We would put fresh treads on at the start of the event, and by the end of the event, there's enough to play the elimination rounds with enough buffer that you're not going to run out of traction. But we would always put fresh tread on per event. In practice, they can go through a set pretty quick. So we really just have a look at it, see how bald they are, and in practice, we run them till they're like the bare conveyor belt backing on the wheels. But yeah, generally one event is a good amount of life to get out of it. Going forward, if it's a predominantly carpeted field, we're going to be using the new like spiky wheels. SDS has them, West Coast has them, but it's like a small nubbed tread that really hooks up well with the carpet. Um, it's a little bit more expensive than tread, but they'll last 2 or 3 times longer and give you better traction along the way. So the new spiky wheels are pretty awesome. More questions? Yes. Yes. Loctite. When you build your swerve modules, you should definitely use Loctite because that's something that you're going to put together once and hopefully not touch again for the rest of the season. The rest of the mechanisms on your robot, if you know that you're not going to immediately have to take it apart again, yeah, use Loctite. That's a great little bit of insurance to make sure that your robot's not going to shake itself to pieces. The question of how tight should I make this bolt is something that students have struggled with for a long, long time. And it takes a long time to get a feel for how tight a fastener should be. I find students more often over tighten small fasteners and under tighten large fasteners. And getting a feel for that just takes a lot of experience. So we actually do have a torque wrench that we got off Amazon that sometimes we'll set up and so that students can feel how tight is tight. But yeah, sometimes we do. Most of the time, we're in a frantic rush to try to put something back together to get it working. Yes. Well, the new Mark Fives have a 2.25 inch wide wheel, and it is a monster compared to the like 1.5 inch ones. The wider wheels have more longevity in the tread, so you have to change them less often compared to the narrower wheels. Um, yeah, so wider wheels, better tread life, better longevity, and a little bit better traction, depending on who you ask. But more questions? Yes. I could give a whole presentation on that. And I actually used to, and I stopped doing it because I had done it for like 10 years at this very conference. So if you go to our website, go to last year's conference slides, I've got a whole talk on the timing of when we arrive at each of those like milestones. Um, yeah, it would take me too long to explain it, but yeah, go to the website. There's the whole video of last year's talk, the slides, everything. No questions. Yes.
We also use April tags and
Oh, during the pre-match checks, we stick an April tag in front of it and make sure that it's tracking, and stick a coral in front of it and make sure that it's tracking the coral. So we test the vision system, we test all the sensors, we test all the things. No more questions. Okay, the next thing in the modern era the next thing that defined the modern era was the release of the Limelight. So 2018, Limelight released the Limelight, and we went from Microsoft Life Cams with a 3D printed ring to vision tracking at 80 FPS. So it really, reduced the barrier of entry to vision tracking greatly. And nowadays we have April tag tracking where you put this magic box on your robot and then it spits out where exactly your robot is on the field reasonably accurately. So a brief note on Limelight versus others. There are other solutions than just Limelight. Limelight is kind of the most commonly accepted one for commercial off-the-shelf options. There are many kind of roll your own solutions where you buy a Raspberry Pi and some little camera modules and stick them all over your robot. And there's Photon Vision is a software that you can install. Um, but there's a lot of stuff you got to kind of do and figure out and hardware to buy and piece together a solution versus just buying a Limelight and sticking it on your robot. So for us, the question of to develop our own vision solution versus just buying one, we're always just going to buy one. And the performance that comes from Limelight is, um, as good as anything that you could do on your own. Questions on vision? I did delved a little more deeply into vision in our programming talk this morning. So the video and slides and everything will be online afterwards. Last year we had a weird thing with our website and they didn't get on forever, but we hope to have that addressed now. So 3D printing and advanced fabrication techniques. Nowadays we have so much stuff available at our fingertips that makes fabricating robots a lot easier. You got companies like FabWorks and Ready Set Cut and Send Cut Send that you can take your SolidWorks or your Onshape CAD file to, stick them in the website. It immediately spits out a price for you, and you can just order it online and have your stuff in like a week. So you can make an elaborate sheet metal robot like one of these, and not have a sheet metal sponsor. And honestly, it's not that expensive to just buy custom sheet metal. When you compare it to the amount of money you're spending to buy 4 swerve modules and Krakens and Canon coders, when you compare that to what custom sheet metal costs, it's really not that bad. So these advanced fabrication techniques are available to all teams, and it has really raised the bar in robot performance. Not only that, but like 3D printing now compared to what it was in 2018, you can go buy one of these Bamboo Labs X1Cs for like $1,200 now and print like engineering grade filaments that are super accurate, robust, um, and make like really elaborate shapes or timing pulleys or gears or a bracket for your camera or the plugs that are in the end of this roller or this whole cradle that holds the coral. Like you can print these really elaborate parts that if you were to try to machine them traditionally without 3D printing would be nearly impossible. So every team should have a Bamboo Labs printer. That's my sales pitch for them. They're phenomenal. And yeah, these advanced fabrication is super common now. Question? Yes. So in build season, we set up for eSun's nylon carbon fiber, and it's a carbon fiber reinforced nylon filament that's very strong and very robust. It is somewhat difficult to print if you don't know what you're doing. Yeah, yeah. So we have 2 bamboos. We have one here, and I have one at home, and they run pretty much nonstop. But we set up and we run that one filament and that one filament only. We don't swap back and forth and have to figure out settings. It's one thing that we do like all of the parts on. And that stuff, that nylon is reasonably high temperature and quite strong, so you can do timing pulleys and not worry about them delaminating. And like the hanger, the brackets for the hanger on that robot are printed, and they're quite solid. We use a lot of those heat set inserts as well for bolted connections. Um, buy the soldering iron tool that's got the different tips for the different sizes, and then just get the aluminum heat set inserts. The aluminum ones are a little bit lighter than the brass ones, so they're also a little bit more expensive. But yeah, printed nylon carbon printed with aluminum heat sets, or you can make some cool stuff. Yes. eSun. It's PS6. It's like $52 a roll for a kilo on Amazon. So it's like it's twice as expensive as PLA, but it's way better. Like if you make a timing pulley out of PLA that runs at a high speed, the teeth will get warm, then get soft, and then you won't have any teeth. And so yeah, all this stuff is that PA6. So yeah. Um, the pinions on the Krakens are aluminum, and then everything else is printed. And we actually printed these before the aluminum ones came in, and we had them on for a while. But the spline, I was kind of sketched out by the spline. But those ones are printed; they're right on the spline. Those ones are much faster and lower load than these ones are, and they were fine all season. So yes,
Do you guys have any like saying because we tried printing with similar filament, reality
yep.
and it wasn't.
Yeah, so the big thing with that filament is you have to dry it before you print with it. And you have to dry it like put it into dry as long as you think is reasonable. And then put it in for like 3 times more than that. It's like so my recipe is 12 hours at like 100 Celsius in an electric oven. And then you have to seal it up, keep it printed in a dry box until the roll is gone. And if it's out for more than a day or two, it'll absorb enough moisture that it'll start printing like crap again. But almost all of the printing issues with nylon carbon filaments are just from not having it dry enough. Um, Bamboo has a heated dry box now, a little standalone one that goes to like 85 Celsius. At 85 Celsius, it'll take like 2 days to dry or roll out. So I have the I think it's a Creality one, but it's actually two rolls of filament wide. So whenever I finish another roll of filament, I'll take a new one out of the bag, stick it in the dryer. It's in there for like 4 days until the other roll runs out, and then I swap over and open a new bag and stick it in. So each one's drying for like 4 days before it actually gets printed. And like 90% of the problems printing it are with not having it dry enough. And then for profiles, we have two the generic PA6 template in Bamboo Labs slicer works really really well. The only thing we did was adjusted the XY hole compensation by like a half a thou to get dimensional accuracy out of the parts. And we can do like bearing press fits and stuff, and it's super dimensionally accurate. There's another question.
Yeah, that's a question. What nozzle?
0.4 millimeter hardened steel. If you have a Creality, there's actually there's a ruby nozzle on Amazon that's like $50 that works really well because it's abrasive and it'll destroy a brass nozzle very quickly. Yes, we don't, but we probably should. Yeah.
I know people just haven't been curious about it, but it's been like classes.
Over the course of the season, it's not too bad, but there's some like random old parts over there that are a couple years old, and if you pick them up, they're like wet noodles. It's really wild.
That's the same.
Yeah, it's the same nylon. It's kind of scary, actually. More questions? I could give a whole talk on 3D printing. I kind of love it. Okay. No more bags. So this was the other thing that defined the modern era. So what did that mean for us? Well, not that much, actually. We still build 2 complete robots. We haven't fundamentally changed our approach to build season from when we had to seal our robots up in a bag. The only difference is now after like week 6, we have 2 robots here instead of one that's in a bag that's in a closet and then another one sitting beside it. So not a lot really changed for us. One thing that's good and bad is the season is now a lot longer than it used to be. It used to be really nice that at the end of 6 weeks, you sealed your robot up and you could breathe for a little bit. Now at the end of 6 weeks, you just have 6 more weeks. So Yeah, the longer season drags on a lot more, and it's a lot more exhausting for mentors to be away from their families and for long nights. So teams need to be mindful to not overdo it. Um, there is definitely such a thing as working too hard, and FRC is not the be all end all of our lives. Um, so yes, be mindful of this. Need to be aware of late season burnout. We actually take all of March break off. Like it's in the middle of the season, and we're generally not competing those weekends. And it's really nice to just not come to the school for a whole week. Yes, our schedule and build season is 4 days a week. So we do Monday, Wednesday, Friday after school, and Saturdays here. And we never go over that. We never pick up an extra Sunday because we're behind or stay late on those other days. It's 4 days a week after school, and 3 days a week during the week, and then Saturdays. So it's like 30-ish hours in here a week, which is a lot. It's a lot depending who you talk to. Like you go talk to Madtown and they're like a 70-hour a week team. And it's like, well, that's a lot. That's more than I want to do. So um, every team's got to kind of figure out what works for them, um, and what works for their team's mentors, and make an informed decision for themselves how much they have to meet, and then design and build their season around that time constraint. Because you don't want to build this like super elaborate robot and then realize that, well, we meet 2 days a week for 6 hours. That's not going to work. So you need to scale back your goals and the complexity of the machine you're going to design according to your schedule. So no more bag means more practice. So at the end of 6 weeks, instead of sealing our robot up and sticking it in the closet, we still have our robot for the next 3 weeks until we get to our event. So we can practice a whole lot more. Well, what does that mean? That means that teams that have a practice facility have a huge advantage over other teams because they still can practice for the next 3 weeks with their robot, and they don't have to like stick it in a van and drive to some field across town that's a huge pain in the butt. So it was good in that it gave teams more time to work on their robots, but it also really benefits the teams that have practice fields versus the teams that don't. The next thing was the elimination of the bill of materials. And back in the day, there was a $6,000 cap for your robot, and no one item could be more than $600. Nowadays, teams spend $6,000 on their drivetrain and still have a whole robot to build on top of it. So robots in general got a lot more expensive to build. Um, yeah, sucks. So now we have unlimited budgets, so we can just like throw Krakens at everything and stick 4 Limelight 4s on your robot, and um, you know all this fun stuff.
Still $600 seems the point.
Yeah. It used to be like $400, so like it's gone up, and yeah, and a Limelight 4 is 5 something US, and then the Halo is sold separately, so that's a separate line item, and it's like stuff is expensive, and that's just life. So now we can have these 16 plus brushless motors, Canivores and Pigeons, and the Canivore and Pigeon are both great products. They're not inexpensive products, but they're very good products. So stuff is just generally a lot more expensive. And the other interesting thing, mid-season rebuilds are now like a thing. You get teams that show up for a regional. Seed number 1, win the regional. Go to another regional next week. Seed number 1, win the regional. Show up to an event 3 weeks later. Brand new robot, which is a little crazy. And these guys pulled it off. 44-14, world class team. Rebuilt the robot mid-season, pulled it off. Einstein finalists. 4 banner seat. Can't say enough good things about this team. But their approach to build season is very different. They literally built an entirely new robot after like week 2 of regionals. So I would caution teams against attempting this unless you have the resources and the drive to do it, because it is a massive endeavor. So what does this stuff all mean? The bomb elimination made 8-motor brushless drives swerve possible. Advanced brushless motion control made swerve drive easier. Published swerve code. Programming a swerve used to be really, really hard. Now there's like literally thousands of examples of Teams code online that you can just like stick on your swerve and get running really, really quickly. Cross-Thread Electronics' swerve drive generator can get you up and running in like half an hour with any of the off-the-shelf swerve drive modules. So programming a swerve is no longer a barrier to entry. No bag and tag allowed for greater development time. So robots are just in general are much more capable than they were a few years ago. And the decreased weight of brushless motors has freed up more weight to build more and more mechanisms. So back when we had brushed motors, you had this like fixed weight cost in just the motors that you can't put lightning holes in a motor. So it is what it is. But now we've got like 20 extra pounds of weight to do stuff with. So we end up with these super elaborate, complicated robots that do wild, wild things. And yes, they're super, super cool. But I kind of miss the simpler days. And off-the-shelf vision made automation more easier. Like this robot would not have been possible 5 years ago. Not even close. It would have been like 40 pounds overweight and auto would never have worked. So what does it all mean? Robots are faster and easier to build than ever. COTS components. You can buy so much stuff now that you couldn't buy back in the day. There was a day when just like getting gears for your robot wasn't a thing. Way back when, teams used to cut their own gears. And if you had a sponsor who could cut gears for you, that was like a huge advantage. Nowadays, it's like go online and you have them tomorrow. Or you just print them and you have them in 40 minutes. So things are a lot different than they used to be. Advanced control is easier than ever because we can just throw a Kraken on there and then we have fancy motion magic that can position the intake and the arm and the elevator, and you can do differential drives and pretty much whatever you can imagine. Teams no longer need advanced fabrication. If you have a basic shop and a 3D printer, you can build pretty much whatever you want. Reliability and robustness are more important than they've ever been because robots are just better. And when your robot dies on the field, it's not very inspiring. So build your robot reliably and robustly. An unlimited weight and ultra powerful motors and no budget limit just gave teams more flexibility to do too much. And that's really the big thing that I want to get across is when teams do too much, that's what ends up holding them back. More often than not, when you see a team that has focused in the scope of their robot on individual things and executed them successfully, that usually brings success. I want to briefly look at the CyberCows robot last year. Was probably arguably the second or third best robot in Ontario. They did not touch algae at all. They could not pick up algae. They could not score algae. And it didn't matter. They were still phenomenally good because they scaled the scope back of that robot. They said, we're going to do just coral and we're going to just hang. And we're going to forget about algae altogether. And it made the rest of the design of that robot much easier. Whereas teams that said, we're gonna do it all. We're going to hang. We're going to do algae. We're going to do coral. They end up, with a much more difficult design challenge to execute on. And if you don't pull it off, then that can be a big drawback. Or you could be successful in the 2025 game many different ways. You could just do coral and be successful. You could just do algae and be successful. You could just hang and be successful. And honestly, when we got to the championship, if there had been a robot there that just did L1s and deep climbed, and that's all they did, that would have been an amazing second round pick at the championship. The championship, we ended up scoring all the L1s because our partners were not the greatest at it. And most teams didn't tailor their robots to scoring on L1 because it was the least valuable place to score. But at a very, very high level in that game, L1 was the difference maker between all the alliances because everyone would fill the reef and everyone would score all the algae, and all the alliances were triple climbing. So the teams that were better at L1 were the ones that were going the farthest. So in the back half of the season, we actually put substantial time and effort into optimizing our scoring of L1, the least valuable scoring task, because we knew that it was going to be the difference maker at the very end. So scaling back the scope of your robot and picking the low-hanging fruit, so to speak, can make great benefits in your overall performance in the season. So what now? What do I do to make my team better now that we're in the modern era? Leverage commercial off-the-shelf parts where it makes sense. If there's something that you can buy versus something that you can make, you're probably better off to just buy it. Be robust. Make your robot strong. Don't break. Don't die. Design and build within your team's resources. Don't design an elaborate sheet metal robot if you don't have a sheet metal sponsor, or if you haven't like made an arrangement with, one of these Sankatsen or one of those places. Those are the resources are available, and you can generally count on them all the time. But if you have some like local sheet metal shop that's like, yeah, we'll cut some parts for you, and then it's week 2 in build season, and you send them some drawings, and they're like, oh, we're kind of busy right now. We'll probably get that in 2-3 weeks, something like that. Well, that doesn't help you. Now you're much worse off than had you just built it yourself. So design and build within your team's resources. Don't neglect the programmers. Programmers need time to figure stuff out. FRC is, as a design challenge, is a systems design challenge made up of mechanical, electrical, and programming components. There are programming problems that are best solved with a mechanical solution. There are mechanical problems that are best solved with a programming solution. So it's important to have a high level look at what it is that you're trying to accomplish. And sometimes a hammer is the best tool for the job, and sometimes a laptop is the best tool for the job. So put some thought into whatever it is that you're trying to achieve and think about it from multiple angles to try to come up with the best solution. And give programmers time to figure their stuff out. Practice, practice, practice. Driver practice is super valuable. It sucks when you get to an event and you have no driver practice and your driver is learning how to drive your robot for the first time in qualification matches. Try to finish early enough that you can spend some real time giving your drivers time at the controls so that they know exactly how that robot is going to respond in different situations. Do less better. If you take one thing away from this presentation, it should be this line: do less better. This robot is a really bad example of do less better. This robot was do everything the best. And it was an unbelievable amount of work, and it was unbelievably difficult to pull off. And our team goals dictated that we needed to do all these things in order to challenge for a world championship. This robot is a much better example of do less better. So the 2024 robot, there was a game challenge. Basically, the end game challenge was called the trap, and it was this like little plastic chute that was on top of a dangling chain that you could put one of these notes into at the end game, and it was worth 5 points. A single note scored during the teleoperated portion in the speaker when it was amplified was also worth 5 points. So the trap itself really wasn't worth all that much. And like 99.9% of teams should not have attempted the trap at all. It was probably the most difficult game design challenge that we've had in FRC because like the geometry of the trap, it was so high above where your robot could hang, and the size constraints of the robot that year made it so that you could only like hang on to a tiny portion of the note in order to stay within the size constraints and still be able to shove it in the chute. So it was this mechanically super difficult challenge that was only worth 5 points. And yeah, it just wasn't worth it. So a lot of teams poured a lot of time and effort and resources into building robots that could score the trap because it was one of the bonus points, ranking points in qualifications, but in elimination rounds, it was just 5 points. And there were other combinations of scoring that allowed teams to achieve the extra ranking points even without doing the trap at all. So during our game analysis, we said the trap is really hard. And if we just ignore it altogether, it's going to make the whole rest of the robot a whole lot easier. So we just ignored it. And the robot was pretty good. If we do a little case study at this robot, we mastered the simple stuff. It was a single jointed arm that went up and down and a couple of rollers that fed the note through the robot. And then the shooter at the front, and then the hanger just was the pneumatic hook that went up and down. So we really just mastered the simple stuff. The geometry of our single pivot allowed us to score the speaker and the amp, which was useful for amplifying the robot. So it was another game challenge that you pretty much had to do. The game piece tracking that we did to pick up these notes, we just used simple color tracking. We didn't have any like machine learning. We had a Limelight 3G on the back of the robot that was looking for an orange blob on the carpet, and we used that to pick up the game pieces in autonomous. We didn't use the 3D bot pose. We just had simple 2D tracking. We pointed the robot at the goal, ranged our goal based on the stuff coming back from the Limelight, and used that to aim the shooter. We had the pneumatic hanger that just went up and down and enabled us to do the like last second after the buzzer hang. And despite the fact that we had no ability to score in the trap at all, we were still the #1 seed at every event we went to with a 3.5 RP average. 4 was the max in 2024. So we still achieved the 4th ranking point in a lot of matches by doing the other things that we could do to get the extra RP. And we only lost 3 matches all season. 2 of them were on Einstein back-to-back, and that was unfortunate. But the season in general was very successful. And the strategic design choices we made to do less better really is what made that robot. This one was good too, but that one was better. From a do less better perspective. Quick thanks to our sponsors. You guys have been a great audience. We'll take any questions you have about pretty much anything. We have a few minutes under time. How about that? So thank you for being a wonderful audience. We can take any questions you guys have now. Yes.
So with the ability of 3D printing all this application stuff, have you noticed any difference in amount of prototyping you do? Like or
To be honest, we prototype very little. So from that standpoint, no. But building prototypes is way easier, which can be good and bad. There comes a certain point where you have to stop building prototypes and just build the robot. So our approach to prototyping is very much an as required process. So if we're trying to figure out the exact geometry of something specific that we can't either leverage previous experience from or visualize from the CAD, then we'll make a quick mock-up to figure out the exact geometry for the rollers to pick this up off the ground, like the height and position of those rollers to pick it up off the ground. We made a prototype that was like 2 pieces of plywood with a couple of rollers and a cordless drill, and then we could play with the position of those rollers to figure that out. But the prototypes are very simple, very janky, to prove out a very specific thing. We generally do it kind of in parallel where we're developing the CAD and we're going, where exactly do we need to put these rollers? Okay, let's go get some plywood and mock this up. We'll spend dozens of minutes on a prototype, figure out the geometry, and then go back to the CAD and use those numbers to fabricate the first revision of it. And then if we need to change it again in the future, or we think we may need to change it again in the future, we'll design it in such a way that we can swap out the side plates on the intake to change the roller geometry and design it with some flexibility that we can move those rollers around if after the first pass we realize that if we did XYZ it would be better for performance or whatever. So we don't do a lot of prototyping up front, but we do a lot of revision as the robot evolves, kind of thing. Yeah. And we try to build the robot very quickly in order to have time to do that rather than spending a bunch of time on a bunch of janky prototypes that may give you misleading results, because a poorly built prototype may lead you down a path that ultimately proves false because you didn't execute it well in the first place. So there's a bit of a trap that you can fall into there with trusting your janky prototypes too much. Yes.
What type of CAD software do you guys use?
So we're a SolidWorks team. We've been a SolidWorks team for a very long time. I've been designing professionally with SolidWorks for like 20 years. So we're a SolidWorks team. The choice of CAD software, there are many options available, and like the two most common ones are Onshape is the biggest one now because the collaboration is great. The cost of entry is less. The performance on not amazing computers is very good. But I'm too old to learn something new, so we're sticking with SolidWorks. But yeah, so we stick with SolidWorks. The workflow depends year to year. But generally speaking, week one, we're figuring out the conceptual design. In that first week, we're doing some to scale 3D sketches of like the side profile of the robot. Of this is generally what's going to look like with realistic space claims for the singulator, and the intake's going to be roughly this big, and this is how tall the elevator is going to be. And sometimes we'll do a kind of block 3D mock-up if a side profile view doesn't allow you to see the geometry and see the space that everything is going to fit well enough. So this robot, we had a kind of blocky 3D cheesy model of roughly the geometry of how stuff was going to work. And the workflow. Yes. We generally in SolidWorks, it's called like in context modeling, where you're making a part that's referencing other things in a large thing. We have 0 in context parts. I don't believe in them. I don't think that's the right way to approach design. But there is like a general layout sketch that is like roughly what the thing looks like. Does that more or less answer your question? Okay. Yes. Generally, it's a very, very small group. Yes, generally it's a small group. The last couple of years, Balraj has honestly done like 80% of it himself. And then, I've done a mechanism here and there, and we've had other students involved depending on their level of capability and their level of commitment with the software. SolidWorks is not the easiest software to get into. And it takes a long time to get proficient to the point where you're not frustrated with learning how to use the software instead of designing the thing that is you want to design. Build season is not the time to be learning your CAD software. you need to be proficient with the software before the season so that you can design things, quickly and efficiently. Um, so we encourage students to do stuff on their own in the off season, so that when it gets into the season, if somebody wants to take on the drivetrain and draw the frame rails and draw the base plate, they can um, they can do that modeling. They can generate the part drawings that are going to go out for fabrication. Um, and so we have some students that do a little, and we have some students that do a lot. Um, and then I do some of it and pick up the slack where, kind of where is needed. And I generally keep an eye on the overall model all the time. So we use Google Drive to sync files between all the collaborators that are working on it. Um, but Google Drive is really bad at having multiple people have a model open at the same time. So generally, if we're doing design, we have a design Discord channel that's a voice channel, and only one person is doing something actively at the same time, unless it's completely separate. Like when we're doing drawings, somebody will have the drivetrain open and they'll be doing drawings for the drivetrain, and somebody else will have the elevator open and they'll be doing drawings for the elevator, but they don't have the whole robot open so that we don't have like file conflicts. And we do that by having a voice channel open, so that if you're working on the robot in CAD, you're in the voice channel, and if somebody's like, hey, can I have the elevator so that I can go fix this whatever, they can quickly close out, make those changes, and then reopen the file and not have any kind of file conflicts.
Usually the best way is
Yeah, with SolidWorks anyways. Onshape I can't speak to, but with SolidWorks, yes. More questions? Yes.
I don't know when you want to start adding. Like when you develop a concept for your robot, how early do you want to start adding is this like your idea, or like potentially move it later, but also start adding more.
As soon as you have a concept that you feel confident in moving forward with, you should start detailed design. And for us, that decision is generally like the Wednesday or Friday of week 1. And then week 2 is like head down CAD, let's go design the whole thing. And then the end of week 2, we were actually early with this one releasing it, but at the end of week 2, we released for fabrication and started fabrication in the school, and the stuff for external fabrication went out to the sponsors. Normally, it would be like the end of week 3, but this one was like a week ahead.
How much, I know that in the past you got sheet metal sponsors,
Yep.
sheet cutting, but now that you've got the Holtzman stuff, how much of that was out? You built, like how much of it was in-house, how much of it was?
So the tubing was laser cut. All of these like small plates and stuff, we're doing these in house. The Lexan stuff is all in house. Any of the turned components that are done on a lathe, they're done in house. The base plate is laser cut outside, and these sheet metal brackets and the sheet metal wrist was done outside. And then everything else was done in house. Like these plates went through 6 revisions before they were done. The intake aligner went through 40, I don't know, a lot. The intake went through a great number. So anything that we think that we're going to have to iterate and revise on, we're designing the robot up front so that we're utilizing the resources we have in-house. And things that we know that will not change, or we don't have the capability to do them in-house, like the really long pieces of tubing, we're sending those out. But the elevator had 0 design revisions from when we built it to, well, now. Pretty much everything else went through substantial revision. Yes.
Is there a drawing packages at the end of
Yes.
that and the fabrication, or
Yes, just with less revisions. So the part drawings we manufacture from the part drawings, and a lot of the part drawings that are in that package are the ones that we went to fabrication with. So our workflow in fabrication, that cart you see there with all those little totes and stuff, that goes down to the machine shop with a big stack of drawings and all the raw material. And then as parts are manufactured, they get checked off in the drawing and they go in that bin. And then they stay on that cart until we start assembly. So there's that whole thing is just full of parts with drawings along with it. And then down here, we do actual robot assembly. We'll make the assembly drawings are often lacking. It's usually done 5 minutes with just like a ISO view of what the thing looks like in the bill of materials. But then at least you can give a student, here's the drawing, go get all these parts. We're going to put this thing together, and they can gather up all those parts on a table and then sit down, put the thing together, and we can have 5 or 6 kids building stuff, and I'm like running back and forth between all the tables, making sure that everyone's not missing a space or putting a bearing in backwards or something silly. So putting putting Loctite on Lexan. Yeah, does that answer your question? Yes. Okay, so the question was, why do we use 1/4-inch rivets versus 3/16 rivets? Well, 1/4-inch rivets are twice as strong. How do we ensure that they're installed properly? We have a big ass rivet gun. um, we have a pneumatic rivet gun that works up to 1/4-inch. Ah, yes. So this big monster is, oh boy. Well, you can see it anyways. That big monster works up to 1/4-inch. We use 1/4-inch because, well, we've had smaller rivets shear. So for the base plate, that's a major shear point, we use 1/4-inch. And we actually bolt the corners too, because we've had those corner rivets start to loosen up or shear over time. So it's really just a strength issue. Why you use a bigger fastener for any application is you want two things to hold together better. More questions? Any more questions from the chat? Yes. Yes.
Have you guys experimented with EPCF as well? I'm just curious because it seems to be about as strong in the different properties, but just it doesn't have the moisture.
To be honest, I haven't tried it. It's PTCF? No, I never tried it. Do you have a good source for it?
I know most of the brands are coming out with their,
Okay.
their own.
Yeah.
Right? F1,
Okay.
but there has been a review that that's what I'm curious because it's as strong as the nylon counterpart, except for what we do.
Okay.
It's like no moisture.
Huh.
So,
Something to look into. More questions? Yes.
For polycarbonate rollers,
Yep.
how do you guys build the plugs?
I'm glad you asked. So the polycarb rollers we had on this robot, it was 1.5 inch 1/8 wall polycarbonate tubing. That comes from McMaster Carr. And then the end plugs are actually just printed nylon plugs that go into the end with an aluminum shaft on the inside, and a bolt that holds the shaft in. So we basically make this hollow roller with 2 little aluminum stub shafts sticking out the end, and the plugs are just printed carbon nylon. And we super glue the end plugs into the Lexan roller, and that's really like a printed plug and a little aluminum shaft, and that's pretty much it. There's a couple examples on the table actually, if you want to have a look at one later. There was another question at the back here. Yep.
What kind of access do you have to this room? I know with it being a school, there might be some restrictions.
So the room you see here is our practice room. We have access to this year round. A custodian has to be in the school, so we book the Monday, Wednesday, Friday, Saturday to have this space available. But during the week, like at lunchtime, kids will be in here practicing with the robot daily during build season. So we have full access to this room, and it's a huge advantage to have this space available to us. We also have access to the machine shops and Mr. Lyon's room and the welding shop and stuff. There's a sheet metal brake down there that we use for like bending Lexan and stuff. And the wood shop has a CNC router in it that we make all these little Lexan bits too. But yeah, we have access to this. This is our space. There's no other class in here or anything. Yes.
Are you still working?
So the exam period, we have a kind of reduced schedule where we only stay till like 4. So that during the exams, they write the exams here like first thing in the morning, and then they're done at like 10. but the school closes at like 4, so mentors don't get here after work. But if kids are done their exams, they can work in the machine shop or do fabrication stuff. Usually we're still in the fabrication process during that exam week, just depending on where the calendar works out. But yeah, we do have a reduced schedule. We don't stay as late as we normally do during exams.
Some ways we actually have more time.
Yeah, like the students have more availability because they can like finish their exam at 10 o'clock and then they have all day to make parts. But the days that we're only here till 4, there's no mentor support. So it's just like a bunch of kids and Mr. Lion like running amok. So um, yeah, fun times. More questions? Yes. Ooh, that's a loaded question. We think about it a lot. Um,
I guess it was too general.
and it really is the general robot architecture that we ended up deciding on this year is really a conglomeration of 4 examples that we saw on Open Alliance or Robot in 3 Days or online resources. We literally just said, hey, if we piece this intake together with this aligner and this kind of elevator like this will probably be pretty good. And there it is. So in our build thread, we actually linked the 4 videos that were like the building blocks that ultimately led um, to that. Yeah, it's a great thread to read through if you have more questions. Uh, they were all like links from Chief Delphi or build like. The problem is there's so much content out there now that it's hard to stay on top of it all. And unless you're like literally browsing Chief Delphi 12 hours a day, it's easy to miss stuff. So there's a lot of teams that are open alliance teams where they share all their prototyping videos and share all their stuff that they've done with the community. And sifting through all of that is kind of the challenge because there's some really technically capable teams that have really, really good examples. But there's also just as many new teams that are doing open alliance stuff that really don't know what they're doing. So it's tough to sort through the vast quantities of information. Um, yeah, browse Chief Delphi a lot. I don't get a lot of work done during build season. More questions? Okay, you guys have been a great audience. Thank you very much. I'll be around.